Hello everyone. So again, welcome back to the latest lecture session, right? So in the last session, we were discussing the approaches relevant to using the redox potential, right, or reduction potential EH, right? And we discussed the relevant aspects and the analogies with respect to PE, right? And then we discussed the reaction feasibility, right, as in when would the EH cell be positive, right, as in EH1 greater than EH2. Only an EH cell is positive, would the delta G then be negative, right? So for that to occur again, EH1 has to be greater than EH2, meaning that I believe what now reduction needs to occur at cell 1, right, and oxidation will occur at the cell 2. Reduction at cell 1 meaning cathode, right, at cell 1, and anode at cell 2, right, for the E cell to be positive and thus the delta G to be negative for the reaction to be feasible. And then we talked about relevant aspect as in an imposed potential. So with respect to imposed potential, there are two aspects that we are going to look at, I guess, right. So let's say if there is a reaction that is thermodynamically favorable, right, but you still want to promote such a thermodynamically favorable reaction, you can again impose external potential to promote this already favorable reaction. And the second case is, let's say there is a reaction that's not thermodynamically favorable now, right, a redox reaction that is not thermodynamically favorable. So, but you want to get it through, or make that your what do we say, the redox reaction that you want to go through, let's say, right, but that is not thermodynamically favorable, right. So what are you going to do now? So you are going to impose an what do we say, external potential, right, so that this particular cell, right, now becomes feasible enough for the electron transfer to take place. Without the imposed potential, right, there would be no electron transfer, but because of the imposed or the external potential that you are going to apply, that is going to go through, that as in the redox process is going to go through. So we are going to cover that aspect now. In this aspect though, it's important to look at, let's say, the terminology, or I shouldn't say the terminology, I guess, the signs that are applied to this external voltage, I guess. And the reason being, in your applied voltage, let's say, right, or the external voltage that you are potential that you are applying, pardon me. So you have the positive terminal and negative terminal. Depending upon to which electrode you connect your positive terminal, right, you are going to have what do we say, promoting or not promoting your current redox process, right. So we are going to look at that, right. So here we have, so the Ecell is going to be equal to delta EH naught minus RT by NF natural logarithm of Q dash of the overall reaction, right. This is something that we have looked at in the past, right, or in the previous session, pardon me, and that is also equal to EH1 minus EH2 now, right. So when you apply an what is external potential, or when we look at the applied potential, so E cell is going to be written as EH1 minus EH2 minus this applied potential, right. But this particular standard form of using this particular negative term here would be contingent upon your positive terminal, right, being connected to cell 1 now, right, and the negative one would then obviously be connected to cell 2, I guess, right. As in, what does this mean? Negative would be connected to cell 2, right, and positive would be connected to cell 1, and then this would be the relevant what do we say, symbols or such that you need to use here with the applied voltage or potential. And let us look at what that is, but we are going to understand what this means. What does this mean now? When you are applying, what do we say, positive, what do we say, the positive terminal, or connecting the positive terminal to the electrode at cell 1, that means you want to promote oxidation, right, at cell 1, right, and that would obviously mean you would want to then promote reduction at cell 2. So when you are trying to promote these conditions, right, this particular what do we say, equation applies, and this is the standard way to look at it, I guess. So we are going to look at it in terms of the cells that we have looked at, let's say. So electrochemical cell, let's say cell 1, and let's say this, right, and you are going to have your cell 2, and let us say this is the direction of your flow of electrons currently now, right. And what does this mean now? Usually we have the cathode here, right. So, cathode here, but that would then be reduction. So, I need to reverse the flow of the electrons here, and this is the anode here, right, anode here, and this would be oxidation, right. And here I am going to erase that here as in the direction of flow of the electrons. Let us say if the E cell is positive as it is, right, yes. So, you are going to have E cell is equal to E1 minus E2, right, and let us say this particular E cell is positive here. So, when it is positive, you know that you will have reduction, let us say at cell 1, that means the cathode, and oxidation at cell 2, which is the anode here in this case, let us say. And in this case obviously we do not have any external potential applied now. So, here we are now going to consider in the second case, let us say when we apply a external potential now. So, I am going to use the term or the symbol with respect to negative and apply it similar to what we had here, right. So, that means my positive terminal now needs to be connected to cell 1, let us say. Let us see what that entails. Yes. So, I have my electrode 1 here or cell 1 and cell 2, right, and now I am going to put in my external, what do we say, voltage, let us say, or applied voltage here, and this is positive and this is the negative terminal, and so that is the positive is connected to cell 1 and negative is connected to cell 2, and let me write that as, let us say, cell 1 and cell 2, right. So, now you know what is going to be promoted now, right. So, in general, you know, here the way you applied this particular terminal or the applied voltage, you see that the electron flow from the negative terminal to the cell 2 will be promoted, and also electron flow from cell 1 to the positive terminal will be promoted, and the electron flow would be within the what do we say, applied battery, let us say, if I can look at that, let us say, will be from plus to minus and minus to plus outside here, right. So, now what am I promoting? I am promoting the flow of electrons from cell 1 to the positive terminal, and again electrons from negative terminal to cell 2. So, now if this E applied, right, the magnitude of it, let us say, is greater than the magnitude of E1 minus E2, right, which in this case I am you know, assuming that it is going to be. Now, the electron flow is going to be reversed from this case, right. In the earlier case we had reduction at cell 1, but now as you see here, the way we have considered the relevant aspects and connected the relevant terminals, we are going to have promotion of oxidation at cell 1 and reduction at cell 2, right. So, now your particular cell 1 is going to be your anode and your cell 2 is going to be equal to your cathode, right. Again that is understandable here again. So, again here let us say if you connect it in reverse, let us say if you for example connected your what do we say now, negative terminal to your cell 1 and positive terminal to your cell 2, then this would have to be written as, or E applied will have to be considered as negative, that is you know, transforming this particular what do we say variable to be overall positive, I guess, right. So, the sign or the symbol, I guess, is remarkably important, and that is relevant to the negative symbol is relevant to the positive terminal being connected to cell 1, right. So, that is something that you need to consider here. So, again we will now look at the two aspects that we have considered or talked about earlier, as in let us say there is already a thermodynamically favorable reaction, let us say redox reaction, and you want to further promote that. So, what are you going to do now? You are going to see to it that the E applied here is going to be negative here, right. So, the E applied being negative, what does that mean now? That you are going to connect your negative terminal to your cell 1 and positive terminal to your cell 2 in this particular example, right. And let us say the second case, let us say a reaction is thermodynamically not favorable now. So, you want to make that particular reaction thermodynamically favorable, right. So, what you are going to do? You are going to have an applied voltage or external voltage, right. And how are you going to have the relevant what do we say variables are set up such that this equation is going to be, right, you are going to see to it that the E applied is positive, right. E applied is positive and greater than in magnitude with respect to the difference of EH1 and EH2, right, or it is going to be the difference, what do we say, have the opposite sign of delta EH, right, and what do we say, greater than the sum of pardon me, greater than delta EH, right. So, let me just write that down. So, the second case, as in there is a unfavorable reaction, right, similar to the example we just looked at, and you want to make it favorable, I guess. So, how do you do that? You are going to see to it that, you know, your E applied, let us say, is first greater than in magnitude of your delta, or let us say I will write it as E1 minus EH1 minus EH2, right, and also the symbol, that the sign is going to be the opposite of EH1 minus EH2, right, and that is when, I guess, obviously you are going to promote a redox reaction that is what do we say, not favorable, and for that case obviously you need to apply higher external voltage and also look at obviously the relevant connections, and for that your E applied needs to be a different sign when compared to EH1 minus EH2, right. So, I guess now we are going to go over and look at a particular example, right, and look at, let us say, in which case would a particular what do we say, half reaction or set of two half reactions you know be favorable, and let us say when you apply an external voltage of a certain what do we say value, how is that going to change, right. So, let us look at that now. So, we will have oxygen at 1 bar, let us say, right. Keep in mind that usually the partial pressure of O2 is equal to 0.21 bar, and let us say the pH 7 in this example, pH in this example we consider to be 7, let us say, and the relevant half reaction we have is oxygen gaseous plus 4H plus, I guess, right, plus 4 electrons go to 2H2O, and then the reduction potential, EH naught standard reduction potential is 1.226 volts, let us say, for this half reaction. This is the data that I have, and we are also going to look at a second electrode, let us say, where 2H plus 2 electrons, right, can go to H2, and this obviously your reference or the standard hydrogen electrode, right. So, that is why obviously the reference, it is obviously set as 1, EH naught is equal to 0. And for, let us say, for a certain set of conditions we are going to calculate the EH values for both these cases, and here too we will consider that H2 is at 1 bar, I guess, right, and let us go ahead and calculate EH1, let us say. So, EH1 is going to be equal to EH1 naught minus, again as we know, RT by NF natural logarithm of Q dash, right, that is equal to EH naught is out here 1.226 minus RT by NF, let us say here N is the number of electrons being transferred, which is 4, right. So, I guess the value of RT at 25 degrees centigrade divided by the Faraday's constant is going to be equal to 0.02569 divided by the number of electrons is 4 into natural logarithm of Q dash, right. So, here you have activity of 1 out here, right, because water activity is 1 divided by activity of or the partial pressure of O2, but in this example we are considering a case when the oxygen is at 1 bar, let us say. So, the partial pressure of O2 and that is 1, so I am going to take that to be 1 here, right, activity measured by partial pressure of O2 here, and because the pressure is at 1, that is going to be 1 here, and H plus concentration is 10 power minus 7, right, raised to the power of 4, right. So, that is why how we have EH1, and that looks like turns out to be 0.812 volts, right. And similarly we are now going to calculate EH2. So, EH2 is going to be equal to EH2 naught minus again RT by NF, and what is this value now, 0.02569 by the number of electrons being transferred, which in this case is 2 into natural logarithm of Q dash again. So, partial pressure of H2 the gas, again we assume that that's going to be equal to 1 bar, right. So again it's 1 here by activity of H plus again because it's at pH 7, it's going to be equal to 10 to the power of minus 7 raised to the power of 2, and looks like with this value is going to be equal to 0.414 volts, right. So here let's just summarize what we have. You have EH1, right, and that's equal to 0.812 volts, and EH2 is going to be equal to minus 0.414 volts, right. So here as we see EH1 is greater than EH2, right. So what does that imply now? You are going to have reduction, right, reduction at electrode 1, right, or which is now going to be equal to the equivalent to the cathode, right, and you are going to have oxidation at 2 or anode, right, and let's see what this Ecell is going to turn out to be. So Ecell is going to be equal to EH1 minus EH2, right, and the values being 0.812 and 0.812 minus 0.414, right, and that's equal to 1.226 volts, right. So again Ecell is positive, right, and that's positive when, as we saw now, reduction at 1 and oxidation at 2, right. So what does that mean now? So O2 plus, let's say, the balanced half reaction 2H2 should go to H2O, right. This is nothing but from balancing these two off reactions. So we have this going through as reduction as it is, right, and then this needs to be oxidation. So we need to swap this particular half reaction and then multiplying it by 2 so that the number of electron transfer is same, or let me write that down here. So O2 plus 4H plus 4 electrons, right, goes to 2H2O, right, and the second one I guess is 2H plus 2 electrons goes to H2, right, and the gaseous here and gaseous here, right. Do we have the right equations? I guess so. And now obviously if this proceeds as reduction, this reaction will stay as it is. If this proceeds as oxidation, we need to swap it, I guess, right. So and then if you look at that overall reaction, right, what is it going to be equal to? O2 plus 4H plus 4 electrons goes to 2H2O, right, and I am going to swap this and multiply it by 2. So 2H2, again gas and gas, right, will go to 4H plus 4 electrons, right, and that's going to be nothing but equal to O2 gas plus 2H2 gas is going to what do we say, or you can think of it as obviously oxygen oxidizing hydrogen or hydrogen reducing oxygen, right, one and the same, and forming water, right. So that's what we end up having here, right, and this is the case that we see out there now, right. So now let's say we are going to consider the case, let's say if we want to, let's say, promote the dissociation of water into hydrogen gas and oxygen, let's say, right. If I want to form hydrogen gas, let's say, so what do I do now? I need to apply, what do we say, external voltage, right, or look at applied potential here, that now needs to be greater than magnitude of 1.226, right, and also what it should also be in the opposite sign. Now let's see what that is, I guess, right. So here let's say we are going to have applied potential greater than 1.226. Let's choose, let's say, 1.5 volts to be our E applied, right, and now how do we apply this? We want to see to it that we promote oxidation at 1, right, and what does that mean? I am going to connect the positive terminal, right, positive terminal to cell 1, right. So then I can write the new Ecell as Ecell dash is equal to EH1 minus EH2 minus E applied, right, and now that's again going to be equal to obviously 0.812 minus 0.414, right, and what do we have that here? minus 1.5, right, and so that's now going to be equal to minus 0.274, right. So what do we see now? Volts. So after applying this external what do we say potential, right, we now have, or we are going to favor the opposite reaction, let's say. So now it's going to be 2H2O dissociating to form oxygen in the gaseous phase and hydrogen, right. Again, how did we go about that? Because we applied an external voltage that's greater in magnitude than delta EH, I guess, right, which is 1.5 volts. And I guess after applying this particular external voltage, now the water is unstable, and then it would now dissociate into the relevant what do we say compounds. And obviously now at what do we say cell 1, you are going to have now oxidation, right, meaning anode. Cell 1 would act as electrode 1 would be the anode, and electrode 2 will now be the cathode, right. Again, just a minor what do we say reworking based on the relevant applied potential, I guess, right. So now we will move on to the next aspect. It is going to be the ORP measurements, I guess, right. So these are the oxidation reduction potential measurements, right. So here out there, let's say, you know, you have commercially available ORP meters now, oxidation reduction potential ORP meters. So what will they help you with, let's say, right. So you, again, this will have a standard electrode, or either standard hydrogen electrode or the submerged calomel electrode or reference electrode, right. And again, it's going to measure the potential difference between the standard hydrogen electrode or the standard or the reference electrode. So how is this ORP going to work? You are going to have a reference electrode, right, your standard electrode, and it's going to measure the potential difference versus a non-reactive electrode, let's say a platinum electrode, let's say, right. And then let's say it's going to be able to give you the potential difference between, based upon the situation in the water, right. Is it more reduced, more oxidized or such, and based on that you can approximate your what do we say EH or PE of your solution now. So in effect, ORP, the ORP meter will give you an idea about the PE or the EH of your solution now, right. So in general, it will help you understand now, is it relatively more oxidizing conditions that prevail or relatively more reducing conditions that prevail in your particular solution now, and based upon that obviously you can tailor that to your needs now, right. But people think of this ORP measurement as a panacea for that will give you all the information that you need, but there are obviously disadvantages in such generalizations. Just let's look at what they are now. So keep in mind that ORP reading looks at the solution, so it's not specific, let's say, to any particular redox couple now, right. So there can be multiple redox couples in the solution, obviously, right. So the ORP meter or this measurement will not look at any particular what do we say redox couple. It's going to be the cumulative one, right, or the PE that's existing in the solution now, right. So that's one particular aspect. And again, the key is that, as you know, redox disequilibrium usually what predominates. So if redox disequilibrium predominates, what does that mean now? Let's say you can still have redox process that are going through, and let's say the PE can change too, right. You do not have or the system is not at equilibrium. So possible that your system is not at equilibrium, right. So combined with this, what is it that we can glean or cannot glean now? So while you can understand if the solution currently has oxidizing conditions or reducing conditions, because the ORP reading is not specific to any couple and is also not what do we say going to tell you if the system is at equilibrium or not, let's say, right, or because you do not know that the kinetics can be slower, right. So what does it mean now? It cannot give you any idea about the speciation, let's say, of various redox couples present in the solution. Right. So this is an important aspect though. So while the ORP will give you a generic idea, it will obviously not what do we say provide you with the relevant information to be able to understand the speciation of the relevant couples in the solution now, right. So this is one other aspect. And now we are going to move on to another what do we say, practical aspect with respect to redox process. So this is with respect to corrosion that you would see out there, let's say, right. So corrosion, again, what is that now? We can understand that again in terms of an electrochemical cell, let's say, right. So we are going to look at that now, right, and we can understand it in terms of an electrochemical cell, right. As in, what do we have in an electrochemical cell? Obviously we have a cathode, right, where we have the reduction taking place. We have an anode, right, where we have the oxidation taking place, right. And obviously what else do we need? We need an external circuit bridging the gap between, or acting as a bridge between the anode and the cathode, right. So external circuit now. So in general, when we talk about what do we say, corrosion of metals. So for example, let's say Fe iron in its zero valent iron, let's say, oxidizing to Fe2 plus, let's say, right. So here anode is your metal, let's say, or the surface of the metal is your anode, right, where the corrosion takes place. Yes. And cathode, obviously, depends upon what is the electron acceptor out there, right. So we are going to look at those aspects. So again, for corrosion to take place, obviously you need your metal surface, right, which acts as the anode, right, where you have what do we say, the release of the electrons, yes, or oxidation. And obviously you need a cathode which would accept, or a place where, or a surface where, or an electron acceptor, I guess, yes, electrode where it accepts the electron or the relevant reactions there. And then obviously you need an external circuit now. So any of these three aspects, if they miss, I guess obviously the corrosion wouldn't go through. So we are going to look at what do we say, a couple of ways to that corrosion goes through, and then look at how we can control corrosion based on the knowledge that we have, I guess. So in general there are two aspects again. One would be with respect to when we have dissimilar metals being in contact. So that's one aspect we are going to look at. And obviously the other aspect is when, let's say, your metal is what do we say, in contact with the usual electron acceptors out there, and the most usual one obviously is your oxygen, and that's the one we usually see out there. But for industrial applications or such, even when we have dissimilar metals, that's a remarkably important issue. I mean, dissimilar metals in contact with each other. So we are going to look at these two sets of examples, I guess. So the first set obviously is going to be the one when dissimilar metals are in contact, right. And so we are going to have an example here. So it's going to be one with iron Fe2 plus 2 electrons, right, and Fe0, and looks like the Pe0 value for this particular half reaction is minus 7.55. And let's also consider another half reaction, dissimilar letter, let's say copper, Cu2 plus 2 electrons, right, goes to Cu, and this particular P0 is equal to 5.74, right. So again here we have the P0 values for two half reactions, and let's assume a case when, let's say, the Fe2 plus and Cu2 plus concentrations are equal to, or activities are equal to 10 power minus 3, and work out the relevant P values and then compare them and see which metal will be oxidized or which metal will be corroded, I guess, right. So let's look at that. So assuming that all the activities are equal to 10 power minus 3, so the Pe1, right, is going to be equal to Pe0 minus 7.55 minus 1 by n, right, and log of what we say activity of this particular what we say metal, right, pure metal. So it's going to be equal to 1, let's say, and by 10 power minus 3, right, and that's going to be equal to 1 by n, as in n is 2. So that's going to be equal to 10 power minus 3, 1.5, and that's 1.5, that's equal to minus 9.05, right. And then the P2 is going to be equal to 5.74 P0, right, minus 1 by n is again 1 by 2, and times log of activity of 1 again because it's not pure metal, right, by 10 power minus 3, right. So again 1.5, 5.74 minus 1.5, so it's 4.24, right. So from here you see that PE2 is greater than PE1, right. PE2 is greater than PE1, right. So what does this mean now? So it means that 2 will proceed as reduction and 1 as oxidation, right. So what does this mean now? When the copper and iron are in contact with each other, you know, one is oxidation, thus iron will corrode, right. Thus iron will corrode, yes. So obviously when you want to control such, what do we say, corrosion due to contact between two dissimilar metals, let us say. So what can you do now, right. So you can have an insulation material between these two dissimilar metals. So what are you trying to achieve there? So this insulation means you are cutting down on that external circuit, right. So here when we are trying to control corrosion, we look at the three aspects: anode, cathode and the external circuit. So when you have dissimilar metals in contact with each other, you can have insulating material between each other, as in you are preventing the contact between them and thus the transfer of electrons, and thus there is not going to be any redox process going through, thus there is not going to be any corrosion of your particular metal, right. Or you can also have a sacrificial anode. Let me just list that, I guess. So how can I control it? One would be insulation, I guess, right, insulating material, and the other would be a sacrificial anode. So you will choose, let us say, another metal, let us say, whose, so it is something like PE2, right, greater than, let us say, PE3, let us say, right. You will choose some other metal and that will act as your sacrificial anode, thus protecting your particular metal, which is iron, let us say, that you want to see to it that it does not corrode, I guess, right. So you are going to provide a sacrificial anode rather than iron acting as your, or the metal surface of iron acting as your anode, right. So that is one particular case. Or you can also, people do that rarely, I guess, in the industries anyway, you can have an applied potential, right. If you have the applied potential, let us say, you can see to it that it is not thermodynamically favorable for this particular, not thermodynamically favorable, I guess. So this thermodynamically favorable reaction does not go through because you are applying a external, what do we say, potential, I guess. So this is one particular way to go about it. So obviously we are also going to look at the second type of corrosion, right. So when you have a metal in contact with a soluble oxidant now, right. So when we have the metal in contact with soluble oxidants such as, let us say, O2, chlorine, HOCl, right, and CrO4 minus, let us say, right. Then again we can have corrosion. So obviously again we can look at, what do we say, the relevant P values, calculating them and so on and go through. But obviously from your background you know that, let us say, O2 is an oxidizing agent, it is an electron acceptor, and again Cl2 and HOCl here, pardon me, right, they are again oxidizing agents, right. So what does that mean now? That their P value will be relatively high, right, compared to most the P values of the relevant half reactions relevant to any other metals out there, let us say. So in that case, obviously what would you observe now? The PE1 being greater than PE2, right. So you will have oxidation of your particular metal. So how can you, what do we say, see to it that you control such type of, what do we say, corrosion now, right. So when you have these oxygen, let us say, dissolved in water, let us say that is in contact with your particular metal now, right. So that is the reason why we paint it, right. Again, that is an insulating material, we again paint it, right, so that we are looking at, you know, cutting down that external circuit which allows for the transfer of electrons from one half reaction to the other, right. So that is the reason we paint metals, let us say, right. Or let us say, you know, you can also see to it that, let us say, obviously depending on the type of metal, an initial layer of corrosion leads to formation of again metal oxides, let us say, and these metal oxides on the surface are again remarkably resistant to any other, what do we say, chemical process or transformation, and they themselves act as an insulating layer, let us say. Or lastly again you can promote formation of, let us say, an insulating layer. In this case I believe we looked at one particular example in our acid base relevant chemical process, right, as in we see to it that you have a layer of CaCO3, let's say, that would precipitate in your distribution network, right. So that would promote, let's say, or not promote, pardon me, that will see to it that your what do we say, the distribution network or the pipeline, let's say, is not corroded. Why is it? Because you have a thin line of your precipitation on your metal here, right. So in such ways you can go ahead and what we say, control your relevant corrosion here. Again, two aspects, more or less we are looking at cutting down or breaking that external circuit which acts as the conductor for electrons from one half reaction to the other. That's again based on the relevant aspects we have looked at here, right. So again with that, I guess we are more or less done with today's session, and we are going to wrap up the class in next session. So in the next session, I guess we are going to look at a holistic approach, right. So thus far we have looked at equilibrium and kinetics, and then looked at the major aspects as in acid base, complex formation, and precipitation and dissolution, and again we looked at redox process. And then as we went through the redox process, we also looked at examples that gave us a holistic idea now, right, as in what would the situation be if you looked at the theoretical aspect of just the redox process, and then as we approach the true situation that we would expect out there in the nature, as in redox in conjunction with precipitation and complex formation, we saw how the system changes and why the relevant background is necessary in our particular chemical process, right. And also throughout the class, especially I guess with respect to, let's say, complex formation, let's say, or precipitation, we looked at, let's say, even in such simple aspects as coagulation and flocculation, why such background is necessary, as in is it charge neutralization that's relevant to your particular coagulation and flocculation, or is it sweep precipitation or co-precipitation now, right, or sweep flocculation or co-precipitation now. Again, depending on that, you need to choose your relevant coagulant, right, Fe2 plus or Fe3 plus, and so on and so forth, right. So again, in the next class we are going to look at it holistically again, just a brief review of what we have been up to, and I guess then we will wrap up this course, and that's it for today, and thank you.